time to start my welcome. I would like to welcome everybody, every participants of our workshop. It's Heteropar 2020, 18th workshop from this series. The previous 11 workshops were organized jointly with Heteropar. This is also organized with Heteropar. The previous one was in Göttingen. I was on this workshop, beautiful city. It was physical conference. Unfortunately, this year we have virtual conference because of this coronavirus pandemic. So it's new experience for everybody. Yes, so it's new experience for everybody to organize such conference in virtual way. It's not so simple. So first of all, my thanks to Heteropar Workshop and Organizing Committee, the main conference. We are part of this very important, prominent conference. And of course, my thanks to Heteropar Program Committee, because members of this committee were responsible for, mainly for, at least for reviewing all papers. And this reviewing is very important, is of critical importance for the success of the whole conference, to provide objectivity of selection of papers. So my thanks to almost all members of this program committee, almost all members of this program committee. Some exclusions were, unfortunately, but almost all work very intensively on reviewing. So also my special thanks to Alexey Lastovetsky from the Heteropar Steering Committee for his help and advice. I am the new person, rather new person in Heteropar. Every another person is responsible for being the chair of the program committee, and to preserve traditions of this workshop is very important. And thank you to Alexey for helping me to preserve this good traditions, to give me some advice in some critical moments, because of this coronavirus pandemic. Some problems happened, and we had to solve these problems. So now about the papers, we have 16 submissions, 17 in fact, because one was withdrawn. The number was a bit smaller, because last year we have 18, but if we consider 17 is only one submission less, but even 16 is, I think, okay in this situation. It's generally the largest workshop. So I think this number is not bad, from 3 continents, Europe, Asia, and no, two continents, Europe and Asia. Yes, Israel, Japan are both in Asia. We had strong reviewing process because only 4 papers were reviewed with 3 members of the program committee, 10 papers with 4 reviews, and 4 papers with even 5 reviews. We had 2, as a matter of fact, we have 2 rounds of reviewing process, because after the first round, we had 6 unconditionally selected submissions and 4 borderline papers, and we organized a discussion using EasyChair, because EasyChair was used for all reviewing and submitting process. And after this discussion, using EasyChair mechanism, 3 papers from this 4th were selected as conditionally. It means that it's my responsibility to check if all remarks of reviewers were taken into account in the final versions of these 3 papers. So finally, we have 9 submissions with the acceptance rates of 56%. It's almost the same as the last year. Finally, it's almost the same. Last year, we had practically the same acceptance rate. So it's all about submission and reviewing process. Of course, again, thanks for these members of the program committee who in this time, partly holiday time, spend their time on reviewing these papers to provide objectivity of selecting papers for submissions. Besides these contributed papers, presentations, we have also 2 keynote speakers, Enrique Quintana-Orti from the Technical University of Valencia, the first speaker, and Tal El-Noon from Zurich, the second speakers. The title of these talks generally devoted to some algorithm and some programming approaches of heterogeneous systems. These talks titles are presented on this slide. We will have occasion to hear, to see these presentations. I think I am convinced that these presentations will be a very interesting one. We will have 4 sessions. Here's the program, a mixture of contributed talks and keynote talks. We finish at 5 o'clock p.m. 17:00. So it's other workshops on Heteropar are half-day workshops, I see, but our workshop is the full-day workshop from 9 o'clock to 17 o'clock. So now some final remarks, important remarks. First of all, about camera-ready papers. 25th September is the deadline for submitting camera-ready versions. Of course, in this LNCS format, EasyChair will be used for this process. I sent you instructions for sending these camera-ready versions, so please be careful about preparing the final version. It's important for the quality of our proceedings. We also plan to publish a special issue in CCP, in Concurrence and Computation Practice and Experience journal, jointly with another workshop, Heterogeneity in Computing workshop. The idea is to invite out authors of selected papers to submit an extended version of their work. It's a bad luck this year, because Jeffrey Fox, which normally was our contact person and editor of this journal, left the journal. He's no longer an editor. We need some time to get approval from the new editor, and I see that new editor is a rather busy man. So to solve all these problems with new editor need some time. But I think that, I hope that this problem will be solved. But we have also some reserve version of another journal. But first of all, we will try CCP journal, because it's a long tradition to publish this special issue in this journal jointly with this Heterogeneity in Computing workshop. This year, this workshop is organized by a rather energetic person, so I think that it will be no good solution to have this issue published together with this workshop. So it's all from my side at this moment. I wish you an enjoyable Heteropar workshop today and the whole Europar conference, in spite of all these coronavirus problems, which change a lot in the whole world, the style of life. Unfortunately, no physical conference. It's different experience, this virtual conference. So thank you for your attention. We could start the first normal session. So now Alexey will be the chair, stop share.
Okay, thank you, Roman. And so our first session is on algorithms and languages for heterogeneous computing. And I'd like to invite our first keynote speaker, Professor Enrique Quintana-Orti. Enrique, could you please share your screen?
Yes, I'm doing it. So
excellent.
Slides?
So it's my pleasure to introduce Enrique to the participants of the workshop. So Enrique is currently with Technical University of Valencia, but previously he had been for quite a while with University of Jaime I, right? Is it correct way to pronounce it? So anyways, it's still in Valencia. So I guess that Enrique is a native Valencian, so he never worked outside Valencia. And Enrique is a very well-known expert in numerical linear algebra and currently linear algebra on many and multi-core architectures. So it's his main interest. He's very prolific, and he has published, I think, over 300 papers, half of which are journal papers. And so he made lots of contribution in his field and well known internationally for this. And he made many different contributions, and it looks like currently he's mainly focusing on linear algebra on GPUs. And the title of his talk is Opportunities for Approximate versus Transprecision Computing in Sparse Linear Solvers for GPUs. So I see a new word here, transprecision. So if it doesn't make a contribution in the field, at least it will make a contribution in the English dictionary. Yes. Enrique, please go ahead.
Thank you, Alexey. Thank you for the nice introduction. And I will explain what I mean by transprecision computing in a couple of slides. Okay. So thank you for giving me the opportunity to be invited as speaker in Heteropar. It's a workshop that I have been participating for many years now, and it's always a pleasure when you are kind of promoted from participant to keynote speaker. So thank you, Roman. Thank you, Alexey, for this. Okay, so now I have to find. Okay, now so. What I'm going to present in this in my slides, well, it's ideas and techniques for what I call what we call transprecision computing. So it's going to be mainly, my presentation is going to be mainly focused on ideas and results. Results to validate, to demonstrate that the ideas that I'm presenting make sense and show some performance or energy. I'm not going to talk about code or implementation too much, but let me say that for all the ideas that I'm presenting in my slides, there is a corresponding code that is part of Grynko. Grynko is a library for sparse linear algebra on main core architectures. It's a modern C++ based high performance library. And the performance is obtained by using CUDA backends for NVIDIA GPUs and HIP backends for AMD GPUs. So for everything that I'm presenting here, there is a code in this library, in the Grynko library, where you can go download the code and try to reproduce these results. Of course, I also invite you to go to the Grynko library and use it for solving your linear systems. It's a very nice library. Okay, so approximate or transprecision computing. This is the slide that I promised at the very beginning. So when I'm talking about approximate computing, I think about an application where precision can be reduced conformal to the application. Unfortunately, this is not always possible. There are applications where there is no permission. You cannot reduce the precision of the result. And even if possible, if you try to reduce the precision, the accumulation of rounding errors may render that your solution has no significance at all. So in comparisons, what I'm advocating here, what I'm trying to promote here is what we call transprecision computing. Instead of trying to reduce the precision of the full arithmetic or the full operations, I want to reduce the precision only of the intermediate calculations, but still obtain a full precision solution. And what I mean by full precision solution has to be explained from the perspective of numerical analysis, in the case at least of linear algebra. So this is the difference between the two terms. Approximate computing, the application allows you to reduce the precision. For transprecision computing, I don't want to reduce the precision of my final result, but I may do it for some intermediate calculation that still not be hard in the final result. So I have to do a short review of floating point formats. This is probably something that you know even better than me, but this will be short, I promise, and it will set the grounds for further discussions in the rest of my presentation. So you know that most of our computers employ what is the standard from IEEE 754 for floating point, which basically formulates three formats: double precision of 64 bits, single precision of 32 bits, and half precision of 16 bits. And these formats define or distribute the bits in a different way. For example, double precision employs 1 bit for the sign, 11 bits for the exponent, 52 bits for the significand. And that gives you a machine precision or machine epsilon that is around 10 to the power of -16. In the case of single precision, the machine precision is about half of that. And in the case of half precision, is well, about the order of 10 to the power of -4. Okay, so in general, we can say that the length of the exponent determines the range of the values that can be represented, while the significand determines how accurate are these values. You may be aware that in the last year, there have been some alternatives to these formats. For example, Intel proposed the brain floating point format with 16 bits, which is slightly different from half precision if you look at how the bits are distributed between exponent and sign. And very recently, NVIDIA, with the new Ampere architecture, proposed what they call the TensorFlow 32 format, which is actually a format that employs only 19 bits, 8 for the sign, 10 for the significand, and 1 for the matrix. So let's talk about the GPUs, and let's look at these floating point formats and the relation to the performance of GPUs. So if you look at NVIDIA generations from 2008 with the first CUDA generation, which was Tesla, up to Ampere, which is the last one, the last generation from NVIDIA, and you compare the compute performance and the memory performance of these architectures, well, from the point of view of the compute performance, there were some difference in the beginning. So double precision, which is marked in blue in my slide, is always the ratio or the baseline. And at the beginning with Tesla and Fermi, single precision was 8 times faster than double precision. That's because of the number of cores that were dedicated to native double precision arithmetic versus native single precision arithmetic. And this has varied along the time. So you see Kepler, the difference was 24, Maxwell, the difference was 32. With Volta, it came back to the usual 1 to 2 for single versus double, but then this architecture introduced the tensor cores. And with that, half precision obtained a ratio of being 16 times faster than double precision. And with a pair, this ratio is maintained. However, if you, instead of looking at the compute performance, you look at the memory performance, the ratio is the natural one. It's single is 1 to 2 versus double, and half is 1 to 4 versus double. So what is important for our case is the compute performance of the memory performance. And my first message here is that for sparse linear solvers, for sparse linear systems, the important is the memory performance, because these are memory bounded operations. So in this case, we can pay a little the price of doing a higher number of flows, because in general, this can be overlapped with the memory. In this case, the memory bandwidth is the important factor, at least for the solution of iterative linear systems. Remember.
Excuse me,
yes,
Enrique, just to confirm, these ratios are performance ratios, right?
The first one are they are all performance ratios.
Speed ratios, I see.
Speed ratios. Thank you. Okay. So again, remember that in my slide about plotting point performance, I mentioned what is the different role of the exponent and the significant bits, and I also mentioned that what is full precision what is a full precision solution, that will depend on the problem. In the case of a linear system, we have to look into the numerical analysis. And the numerical analysis gives us what is known as the rule of thumb for the residual solution. So assume that you are solving the linear system AX equals B, and you compute an approximate solution X star. This X star is what the computer can give you after applying a certain algorithm to this problem. So the residual from this solution, that's the norm of X times X star minus B, the relative residual of this solution is going to be approximately equal to the unit rounded off, which is the machine precision times the condition number of the linear system. So full precision, what I mean that full precision, this message is saying is that a full precision solution can only be as good as the condition number of the linear system dictates. So, for example, consider a linear system with a condition number that is 10 to the power of 4. So you use double precision and start with an initial solution that has a residual norm of 3 order of magnitude, 111.12. And after about 1,200 iterations, you get a solution that is 5 to the power of minus 10. So the accuracy improvement that you can observe between these 2 points is 10 to the power of minus 12, which is basically the product between the machine precision, which for double precision is 10 to the power of minus 16, times the condition number of the problem. And no matter how much you further iterate, you cannot get better than that. So if you go to single precision instead, and you apply the same algorithm, but now you operate all your data in single precision, you do all your arithmetic in single precision, the improvement is only 10 to the power of 4 instead of 10 to the power of 12. And that's again dictated by what is the product between the machine precision and single precision in this case, which is about 10 to the power of minus 8, times the condition number of the system, which is the same, is 10 to the power of plus 4. Okay. Now, this is important in case we start going with a much ill-conditioned, much worse problem from the point of view of the condition. So this is a problem, this is a matrix that is called Apache 2 from the Sweet Sparse benchmark collection. And it's a problem with a condition number that is 10 to the power of 7. And if you look at the solutions, for double precision, the solution shows an improvement in the accuracy of 10 to the power of plus 9 after 6,400 iterations, approximately. While in single precision, you see no improvement at all. That's because the conditioning of your problem is about the same as the single precision accuracy. And that means that if you apply single precision to this problem, you are not going to get anything useful from it. So this is important to take into account when you are applying things like techniques that are related to transprecision computing. You have to take into account what is the condition of your problem, because otherwise the transprecision technique that you are applying may make no sense, may give you no. So two messages to get away or to take away from this first part. The performance of memory-bound algorithms is independent and scaled with the index of the formal complexity. That means that the with memory-bound algorithms, important is memory bandwidth, and therefore the savings that I can get or the acceleration that I can observe for this memory-bound algorithm will come from a reduction on the number of memory accesses. And the second one, for linear systems, you have to be careful with what is the condition number of your probe. Because if the condition is too high, you may not get any gains from applying some transprecision. So what are the 4 transprecision techniques that I want to review with you? So the first one is very well known, is mixed precision with relative refinement. There's nothing new here. The other 3, dynamic precision is stationary solvers, adaptive precision, block-Jacobi preconditioning, and compressor formula basis for TM-RES are new techniques that are integrated into Grynko. All of them are integrated into Grynko, and I will show you that they give some significant savings. So for the first one, mixed precision with iterative refinement is something very, very old. The first implementation of this technique dates back to 1948 by James Wilkinson. And there's a nice review of the different implementation of this technique in Nick Hyam's book about the numerical instability of numerical algorithms. So what is the idea? You start with an initial guess X to your problem, compute the residual in full precision, solve the system for the solve the alternative system for the residual, this A y equals R for y, but you do this in double precision. And then with this solution for this alternative system, you update the solution of the initial system. And you perform this until a certain criterion is satisfied. So the key or the trick here is that most of the arithmetic is going to be done in low precision when solving this alternative system for y, for the variable y. Okay. So with this, what can you get? So you look at the previous problem where we were applying double precision or single precision to this ill-conditioned problem, the Apache 2 matrix. You may remember that in double precision, we could go all the way to 10 to the power of 9 in the accuracy improvement, while we observe no improvement at all for the single precision case. So let's try to apply this iterative refinement in this case. So look at the results now. This is on the left side, you have double precision with iterative refinement. On the right-hand side, you have mixed precision with iterative refinement. That means that you are mixing, you are using both double precision for the outer iteration, what is known as the outer iteration, and single precision for solving this alternative system. And you see that basically we can get the same accuracy improvement in both cases, up to 10 to the power of 14 for this case, which is even higher than what you could expect from the conditioning of the problem. But that's because of the nice properties of iterative refinement. The only drawback for the mixed precision, the mixed precision iterative refinement gives you some runtime improvement. It's not much, about 16%. And it has an important drawback is that mixed precision iterative refinement requires 2 copies of the matrix. One is stored in double precision and one is stored in single precision. And the message again is, remember that all savings are not coming from the fact that I'm doing my arithmetic in single precision. They are coming from the fact that I am accessing the data in single precision. I'm only retrieving 32 bits per element from the memory. Okay. But again, this is an old technique. I say that it dates back to 1948, but there has been a lot of work along the time on implementing this technique on different architectures like FPGAs, GPUs. With the recent advent of the floating point 16 of the precision, there is even a work on using 3 precisions for iterative refinement, half, single, and double. Okay, but as I say, nothing much new here. So let's go to something that I consider to be newer and more related to transprecision computing. And the first idea that I want or the first technique that I want to describe here is the dynamic precision for stationary solvers. So I'm talking or I'm targeting here a type of method that are iterative solvers. And a particular characteristic of all these solvers is that they provide estimates of the exact solution that gradually approach the exact solution of the problem. So one can think, well, even that at the beginning I'm very far from the exact solution, and little by little I approach it, can I operate in low precision at the beginning while I'm still far from the exact solution and increase the precision as I converge to the actual solution of the problem? Well, this is not exactly new. The new part is, or the new part that we propose here is, are the following. First, at least for stationary solvers, we want to decouple arithmetic from storage. The idea is we will store the data in high precision, but we will access only the part of the data that we need. Why? Well, the reason is that we don't want to keep multiple copies of the matrix. We don't want to keep multiple copies of the data. So we only want one copy of the data, but we will access only the single precision or the double precision part of that data as needed during the iteration. And a second important aspect is that given that arithmetic is not what is dictating the cost of our algorithm, we will perform all arithmetic in high precision. We don't care about the cost of arithmetic, remember. We only care about the cost of memory bandwidth, of the memory access. Another important aspect is that we will check the accuracy of the components of the solution element-wise. So we will decide for each one of the elements of the solution whether the current precision level that is being used is enough or it has to be enlarged. And for that, we need an inexpensive criterion to detect when to increase the precision element-wise for each one of the individual elements. So a very short review of stationary solvers. By stationary solver, in this case, I mean the Jacobi solver, which for a given system AX equals P is very simple. It just has to just construct a sequence of solution of approximate solution, where each one of the terms in this iteration is just constructed by a matrix product with this matrix M times the previous solution. And then there is a diagonal scaling or a scaling of the right-hand side B times the diagonal of the original matrix, or the inverse of the diagonal of the original matrix. And well, what are the characteristics of this solver? Well, it provides linear convergence provided the spectral radius of M is smaller than 1. That's a drawback of this problem. Well, on the other hand, the advantage of this method is that it is completely parallel. The only basic operation that requires is a matrix vector product, which is a completely parallel operation. And well, for general systems, it's not too efficient, but it can provide a very fast method for solving the triangular systems that appear when you are applying an ILU precondition. So you don't want to use a Jacobi solver for a general linear system, but there are certain aspects, certain problems where a Jacobi solver is a very efficient method. And in these cases is where we can benefit from properties of these solvers, such as the parallelism, the parallel nature of this method. So now, a key to adapt or to provide a dynamic precision implementation or realization of this Jacobi solver is to detect when we have to increase the precision element-wise. And for that, we are going to exploit something that is the component-wise contraction property of this solver. So consider two consecutive estimates of the solution, xk and xk plus minus 1. And the I component of these two solutions. That's xi super k and xi super k minus 1. Well, the contraction property tells you that because of the linear convergence, there is a parameter or a scalar theta I such that it bounds linearly the distance between the two consecutive solutions to the problem. And this property is what we are going to exploit to detect when to increase the precision for an element of the solution. In particular, if we look at the ratio defined by CAK as the difference between two consecutive, element I of the solutions K-1 and K-2 divided by the same element from the solutions K and K-1. So this ratio should be constant and should be an approximation of this parameter theta, this scalar theta. So what we are going to do is we are going to check whether this ratio is fulfilled, is satisfied, because if it is not, this is a clear indication that the convergence of the component in the current precision can no longer be maintained. And that is an indication that we have to increase the precision for this current component. So this is the trick, this is the property, this is the technique that we are exploiting to detect when to increase the precision for a particular component. From the actual, from the practical implementation point of view, there are some aspects to take into account. First is probably we don't want to check this every iteration because it then detecting whether to increase the precision or not becomes too expensive. So we can do it every certain number of iterations, every 10 iterations, for example, to reduce the overhead of checking whether we have to increase precision or not. We have to take into account rounding errors. So rounding errors can also create or render a deviation from this ratio, from this theoretical ratio. And finally, we want to select a good parameter that avoids stagnation during the iteration. So these are the practical aspects that are described in detail in an associated paper that we'll mention later. So just to take into account that, well, the theory is nice, but the practical implementation has something some aspects to take into account. Another aspect that is more related to the implementation on GPUs is how to access the data in different precision. So I mentioned that this is a solver that starts by accessing the data in a low precision, and as the iteration converts to the solution, we increase the precision. The question that I mentioned also is that I want to keep multiple copies of my data. So in the case of GPUs, what we designed is something that we call customized precision data segmentation. So for example, if I have my data in 64 bits, that would be the figure on top of this slide. I will divide that into two segments, each one of 32 bits. So in case my solver has to access an element in single precision, I will access only the head of the segment. In case it has to access a 64-bit in 64-bit precision, it will access both head and tail, both segments. And this idea can be generalized to 4 segments. So notice that when I do this, the 2-segment case is not exactly the same as IEEE single precision, because the number of bits that I'm using for the head, for the exponent, and for the significant are not exactly the same as in IEEE. But well, IEEE is something nice, it's something that has hardware support, but as the important part is only how I access the data in memory. In memory, I'm free to access the data in whatever format I want. I am free to store the data in any format that I want, and I'm free to recover it from, in any format I want. I just have then to transform from my own format to IEEE single precision. But that's arithmetic, and that has no cost compared to the memory access, remember. So what are the savings? Well, this is a plot that shows for a Jacobi solver applied to a 27-point extensively fixed fixation of a Laplace equation. In the case of the 2 segments, how many iterations are performed in each one of the precisions? So for example, the white part of this left-hand side plot shows how many iterations are performed in single precision for each one of the components. That's the y-axis for each one of the components, and how many iterations are performed have to be performed accessing the full data, the 64 bits of the element. That's the blue part of the left-hand side plot. And in the case of 4 segments, that's the right-hand side plot, you see 3 colors, white and then 3 different blues. And this corresponds to how many iterations the data can be accessed in 16, 32, 48, and 64 bits. So this is just how the data evolves, how the precision has to be increased as we converge to the solution. In this case, the solution is reached after 3,500 iterations. And well, from the point of view of performance, in an actual implementation on GPUs, we show here what is the performance of the dynamic precision variant of the Jacobi solver versus an implementation that operates all the time in 64 bits. These are the results on an NVIDIA Volta GPU. The left-hand side table shows our implementation with 2 segments, and the right-hand side shows the implementation with 4 segments. So let's look at the 2 segments case. You see that this is a ratio, and there are numbers that are below 1 and numbers that are above 1. So those numbers above 1 show that there is an actual acceleration with respect to the double precision, to the conventional double precision implementation. And that acceleration can be up to 30%. The actual acceleration depends on how many non-zero entries are per row in this problem, and what is the residual norm stopping criterion that you set for the problem. So you see that in some cases, well, when the number of elements is very low, the dynamic precision realization does not give you much. Actually, you lose performance, but in a majority of cases, you see that there is some gain to be obtained. So with that, I finish this first the description of this first technique about transprecision computing, and I now move to a second idea about how to apply transprecision computing to the iterative solution of linear systems. So for this case, I will describe how to adapt the precision in block-Jacobi precondition. So the idea is the following. All iterative solvers include, or most iterative solvers benefit a lot from using a preconditioner. What is the idea of a preconditioner? Well, imagine that you are solving the problem AX equals B. You want to find a matrix P that is close, with an inverse that is close to the inverse of A, such that instead of solving AX equals B, you solve an analogous system, P inverse times A, X equals P inverse of B. Why? Because if the inverse of P and A are very similar, then the system is very well conditioned and your iterative solver will converge much faster. Now, given that the preconditioner matrix P is just an approximation of A, why should we use a full precision preconditioner? Why can't we use an approximate preconditioner that operates in lower precision? And that's the idea. The idea is I will use a preconditioner that is stored in low precision, and that will save me the cost of accessing the full precision preconditioner. However, I will perform all my arithmetic in double precision. That avoids the accumulation of rounding errors. And well, even if I perform all the arithmetic, remember that the important part is how is the data stored in memory. What is the cost of accessing the memory and the data in memory, not the cost of the arithmetic. So we did this for a block-Jacobi preconditioner. That's a very simple preconditioner. If you think of the traditional Jacobi preconditioner, is just you just select the diagonal of the matrix and select P as the diagonal of this matrix. In the case of the block-Jacobi variant, what you do is you select the blocks of the coefficient matrix of the system, and that's your preconditioner. So your matrix P is going to be the blocks of the diagonal of the diagonal blocks of the matrix. So the trick here is, well, given that the preconditioner is P, how do I store each one of these blocks? And the technique that we exploit here is that we store each one of these blocks depending on their condition number. So we don't use a single precision for all blocks. We instead adapt the precision of each one of these blocks to the condition of the block itself. And we use different precision formats. So we use actually three length, 16-bit, 32-bit, and 64-bit. And for each one of these blocks, because I have complete freedom of how I store my data in memory, I can select whether I dedicate 5 bits to the exponent, 10 to the significant, or 8 bits to the exponent, 7 to the significant, or 11 bits to the exponent, or 4 to the significant. So I have complete freedom of how I store my data in memory. It's only when I bring the data into the process of registers that I have to transform that to double precision before operating. So what are the savings from this technique? So this is, I will show you some of the theoretical savings by going little by little in over 3 slides. So this one case, the Apache 2 matrix, and if I look at how the blocks are stored, in this case, all the blocks of the preconditioner can be stored in half precision as determined by their condition number. So if I look at another problem, for example, this is another problem for the sweet sparse matrix collection, I see that because of the conditioning of the blocks in this preconditioner, half of the blocks have to be stored in about double precision, and half of the blocks have to be stored in single precision. So in general, we can see for this large number of problems that in many cases I can store all blocks in half precision. In some of them, I can store all the blocks in single precision, and in others, there is a combination between half, single, and double, depending on what is the conditioning of the problem. So, but these are all theoretical savings. This is all, or this just tells me which blocks I can store in half precision, and therefore I only have to recover 16-bit elements from memory. What are the practical gains from this? So this is a plot where I show an actual implementation on NVIDIA Volta GPU of this adaptive precision block-Jacobi preconditioning integrated into the conjugate gradient solver. So the red dots is the speed up of the adaptive precision block-Jacobi preconditioner versus a conventional preconditioning that operates all in 64 bits. So what we would expect here is that because of the adaptive precision preconditioning, I may be losing some precision, and therefore the number of iterations from my solver is larger. So we can see that basically there are only a few cases where this happens, where this occurs. There are only these 3 cases where the number of iterations is considerably higher for the adaptive precision preconditioner, and for the remaining ones, basically using an adaptive preconditioner has no effect on the iteration rate and the convergence rate. On the other hand, if I look at the time, that is the execution, the performance, so these are the green dots. And what I would expect is that the adaptive precision preconditioner, because it has to access less data in memory, it gives us a faster solver. And that is actually the case for many of the problems, except for these 3 that I mentioned before earlier, where the number of iterations is much higher. So basically, what we can see is that many of the points are on top of this line, of this green line, that shows that this adaptive precision preconditioner gives me a solver that is about 20% faster. Okay, so again, I have just shown you a technique for a transprecision technique that apply to, in this case, to a block-Jacobi preconditioner, give you some accelerator. The third technique is that I'm going to describe is particular of a solver, GMPRES, an iterative solver for general linear systems. And what we are going to do here is compress the orthogonal basis for this. So the GMPRES solver is quite involved, it's quite complex. Basically, these are the main operations that you can see in an implementation. There is a sparse matrix vector product and the application of preconditioner. There are a couple of general matrix vector products, general in the sense that the matrix that appears here is dense. And then at the very end, there is a small linear least square problem that has to be solved, but this is basically something that is done incrementally and can be and does not contribute too much cost to solve. So what is the basic idea for this compressed orthogonal basis for GMPress? Well, the basic idea is that in GMPress, you have to determine what is the search direction. This is an utilization process where you are trying to find a solution, and you have to find what is the search direction for this process. So given that this is a search direction, can we just use an approximation of this search direction? So that's equivalent to storing the orthogonal basis that is using in the solver in reduced precision. So instead of using a 64-bit storage for this matrix B, we are going to store it in lower precision. For example, in 32 bits or even 16 bits, and see whether that gives us an advantage. So that's the idea, as I told you. And now let's see what is what are the benefits and drawbacks of this idea. So as I told you, for the compressed basis, I can use different precisions. I can store it in 64 bits. That would be the conventional way of implementing GMPress. I can use it, I can store it in floating point in 32 bits, in floating point 16 bits, or I can even store it in fixed point formats. For example, using 32 bits and 16 bits. And what are the results showing me? Well, from the point of view of accuracy, what I see is that using 16 bits, well, it can be a good idea in some cases, but in others it is not. So for example, here using 16 bits in this KY example gives me a much worse solution from the point of view of accuracy. While in many of the cases, 32 bits is good enough for storing the orthogonal basis. So I don't need to store the orthogonal basis in 64 bits. I can store it in 32 bits. And from the point of view of accuracy, I get exactly the same solution. So what is the iteration overhead? So that means, well, I can get the same accuracy in the solution, but how much I have to iterate? So what I see here is that basically with 32 bits, I can iterate, there is no iteration overhead. I can iterate the same number of times as with 64 bits. So there is no performance penalty here from the point of view of number of iterations. And what about performance? Well, this is performance compared to the standard 64-bit iteration implementation. This is a very busy graph. So if I can summarize it as here. What you see here is the speed up. On the left-hand side, you have the relative number of iterations compared with a conventional 64-bit based implementation. On the right-hand side, you see the speed up. And the speed up for the 32-bit implementation in floating point and integer 32 bits shows that it's about 40% faster than the conventional implementation. And well, in the 16-bit formats are not faster, and that's directly related to the number of iterations that the higher number of iterations that they require. So just to conclude my presentation, the messages that I wanted to convey here is that the speed up in iterative solver for a sparse linear system relates or is directly dictated by the memory bandwidth savings. One important factor here is that, well, our processors are very limited in the arithmetic precision format that they support. However, from the point of view of storage, we have complete freedom on how we want to store or maintain the data in memory. And it is important to use customized precision for memory operations, but always taking into account what is the conditioning of the program. If you are interested in these topics, I have an open position starting in October 2020, where it's a Marie Curie Sloveskaya ITN network, where it's called Approximate. And if you are interested or think that some of your students may be interested, please send me an email. This is a joint work between IIT, the University of Tennessee, my former university, Jaume First in Castellón, and my current university. and it's supported on the German and US side by the Energy Department of Energy, and in the Spanish side by the European Commission through a H2020 program. And finally, all this transprecision effort that we are doing is also adopted by the Department of Energy in the US, and is being integrated into different solvers like Trilinos, Slate, Betsy, Magma, HighPer, and of course Grynko that you might have heard. So with this, I close my presentation, and I'm open to questions from the public. So thank you very much again.
Thank you, Enrique. So virtual applause to you. It's a very interesting talk. And please, questions. So you can use Slack to, I think, ask questions or raise your hand. And you can use chat as well, I suppose. So, okay, while people are making their mind, I have one question to start. To warm you up a little bit. Enrique, so can you explain a little bit better, how is it no overhead when you do computations on the, when you extract single and double precision from double precision format for computations?
Yes, okay, so of course there is an overhead. The overhead comes because you have to transform the exponents. In single precision, in IEEE single precision, the exponent is normalized in an excess that is different from the one that is used for double precision. Mm-hmm. But this overhead is completely overlapped with the memory accesses. So because the cost of memory access is so large, you can overlap these data transforms.
I see. And so this is done by you. You implement this, or there is some kind of?
In many cases, you have when you are, especially when you are employing your own, precision formats, customized precision formats, you have to do it yourself.
Okay.
In case that you are employing standard formats, for example, you want to transform from single precision to double precision IEEE. You just use the cast operations from the lab.
I see. And a related question, so will it work for CPUs?
Yes, some of these techniques have been applied to GPUs. So Grynko is a library that is especially optimized for GPUs, but it also has a backend for CPUs that employs OpenMP, and this technique will also work for CPUs.
Mm-hmm. And another question is, so did you do any work on, so when you apply this dynamic or your transprecision approach, so did you do any work on the proof of correctness of what you do?
No, because
it's all experimental results, right? So
because these are experimental, because these are iterative solvers, we have the benefit that if we introduce some perturbation in the solution process, because they are iterative solvers, they kind of self-heal themselves. So they have this property of self-healing. So if we introduce some perturbation, what we can expect is that the number of iterations may be slightly larger, but the solvers will still converge to the solution.
So you proved the correctness, so which means...
Well, I experimentally proved that
So experimental, but you didn't prove the optimality, right?
I don't theoretically prove the
so you didn't do this work. I see. Okay, so my curiosity is satisfied, so very interesting work, and I'm still waiting for questions from the participants. So any questions for Enrique? I don't know, is it because of the format or it's just everything is clear? Then I have to thank you, Enrique, very interesting talk, so I'm impressed. And I suppose everybody is impressed as well. Thank you very much. Okay. If I was a PhD student, I would be interested to join.
Hello, there was one question in Slack, I think.
I don't see.
I have a Slack open here, and
I have my Slack open. I don't see any questions.
In Heteropar, can you see?
Heteropar. Okay.
Could you discuss?
Yeah. So, could you discuss the performance of the adaptive precision block, Jacobian preconditioner, and GMRS specifically for ill-conditioned matrices?
Yeah, so thank you for the question. I think it makes a lot of sense to ask this. So remember that for block-Jacobi, we adapt the precision of the blocks to the conditioning of the problem. And well, we adapt it to the conditioning of each particular block. So you may have a very ill-conditioned matrix, but the diagonal blocks of the matrix may do not have to be ill-conditioned themselves. So we have two decoupled problems here. One is what is the ill condition of your matrix, and the other one is what is the condition of the diagonal blocks. So even if you have a very ill-conditioned problem, the diagonal blocks may not be ill-conditioned. So it's very difficult to know exactly what will happen for the block-Jacobi precondition. But remember that even if the diagonal blocks are all ill-conditioned, the block-Jacobi precondition will just employ the double precision version, and therefore it will not be affected by the conditioning of the blocks. For GMRES, I cannot tell exactly what will happen for a conditioned matrices. What I can tell is that we have tried it with a large number of matrices from the Sweet Sparse benchmark collection, and some of them are ill-conditioned. And even in these cases, we don't see that the important part is what is the search direction. The search direction is telling you in which direction you should move, but this does not contribute to the how good is the solution. Only it contributes to in which search direction you are moving, and therefore it may affect what is the number of iterations that you require for convergence, but not the quality of your iteration. So that would be my general answer to this question.
Yes, so thank you from Pore Sabri. Next question is, thank you for a great keynote. When using the customized precision format in general, is there a penalty in the arithmetic performance relative to using IEEE format?
Okay, so remember that we do all arithmetic in the three transprecision techniques that I propose. We do all arithmetic in double precision and using IEEE 754 format, because that is the format that is supported by your hardware, and we want to use our hardware to do the arithmetic. What we do is we decouple the storage. We store the data in memory in our own customized format. We then bring this data into the processor register, and we then transform from this customized format to a standard IEEE format. So yes, there is an overhead in this, but because of the cost, because the cost of accessing the data in memory is so high, whatever cost it takes you to do this transformation is going to be completely overlapped with the cost of the memory access. So yes, there is a penalty, but it is overlapped. This any kind of there's an overhead, but this overhead is completely overlapped with the cost of bringing additional data. So memory, floating point of arithmetic, they can be done at the same time. They can be overlapping time, and therefore, in this case, for this sparse iterative solvers, the dominant part is the memory accesses, and therefore, we don't care too much about the overhead introduced by the arithmetic.
Thank you. And I think, I'm afraid we don't have more time for questions, so that's it. Unfortunately, I cannot recommend, and he was thanked for the explanations by Sam Casworth. Unfortunately, we cannot have a continued discussion in the coffee area during the break, but thank you very much. And we are moving to our next talk. So
okay,
can you please, thank you, Enrique. Great talk.
Okay, thank you.
And could you please, so do we have the presenter of the first regular talk? If you do, could you please share your screen? Okay, so it looks like it will be Stefan Groth presenting this talk. So the title of the talk is HighPerMeshes, domain-specific language for numerical algorithms on unstructured grids. So please go ahead and.
Thank you very much. Let's go to presentation view. You can hear me fine, right?
Yeah, now I can. Yeah.
Okay, great. Welcome to my talk. As mentioned, my name is Stefan Groth, and I will be presenting HighPerMeshes. But first off, I want to start with a bit of a motivation for what we are doing in HighPerMeshes. So solving partial differential equations is a very important task in the natural sciences and engineering. And one way to do this is with iterative matrix-free algorithms. And so the domain of HighPerMeshes are these iterative matrix-free algorithms. And here, down here, we have an example of something that you might want to do. First up, let me explain the names that I'm going to use in this talk, right? We have a mesh, and a mesh consists of entities, right? And entities are vertices, edges, right? And triangles, which I will also call cells. And so a mesh is an unstructured grid, and something you might want to do in your solver is that you iterate, for example, over your edges that do not lie on a boundary, and you will somehow want to compute something for these edges regarding the data corresponding to the cells that neighbor these edges, for example. And on the boundary, you want to do something else. But as you can see, this is a very small mesh, right? And in reality, you have millions of entities, and so it makes sense to parallelize and distribute such codes. But the complexity of being able to implement a solver like this, but also being an expert on parallelization strategies is very high, and therefore we need an appropriate abstraction level, right? And I think that HighPerMeshes fills this gap. So what is HighPerMeshes? HighPerMeshes is a domain-specific language that is embedded in C++ 17. 17 is kind of important. We can, there's some stuff we can only do in 17, but this is more for the C++ experts, I guess. And as I mentioned, the domain are these matrix-free algorithms on unstructured grids. And we have certain language features that allow us to implement such a solver, which are meshes, buffers, dispatchers. I will get into this on the corresponding slide, and then kernels on your mesh. And I want to go through all of these language features so you get an idea of what HighPerMeshes is. So first off, we have meshes, right? Unstructured grids are described by connectivity lists, and the main thing to note about unstructured grids is that their indexing does not give you any information about their physical locality in the real space, right? And I will explain this a bit more later. And in HighPerMeshes, you can just initialize them directly or read them from a file, right, for numerous formats. This is not that interesting. What I want to point out here is that our interface provides a mesh which consists of entities, and these entities have a topology and geometry that describe them. To give you a quick idea, topology just gives you information about the connectivity of the entities, like in a graph sense, while the geometry gives you information about the real physical properties of these entities, like physical position, for example. And what you could now do is implement a topology or geometry yourself, right? And it would still work with our domain-specific language. While in this talk, I will only explain, I only have examples with triangular meshes, right? You could still think about quadrilateral entities and it would still work in the DSL. Okay, this is what I wanted to point out about meshes. Next up, let's get to buffers. So to do some useful calculation, you have to somehow store data, right? And the idea in HighPerMeshes is that you can reserve so-called degrees of freedom for each entity. What this means is that you will get some amount of space for each entity of a specific dimension, for each entity of a specific dimension of a specific data type. So down here, we can see an example of this. First off, we have this runtime here. This runtime essentially is an aggregate of technology, right? What this means is that if you want to parallelize your code, you need a certain backend, and this is initialized in this runtime here. And this just hides initialization complexity from the end user. And then here, but what is more important are these degrees of freedom here. And in HighPerMeshes, we have this make DOFs. So essentially what this tells you is for a two-dimensional mesh is that we want 0 degrees of freedom for vertices. We want 1 degree of freedom for edges and 2 degrees of freedom for triangles or cells. And this 3 here is a so-called global degree, so a degree of freedom. What this means is that this is meant for some global constants, right, that you have access to independently or independent of your current entity. And then you can design initialize a buffer of floats and then give them a mesh and degrees of freedom in this example. And this is how you initialize buffers in HighPerMeshes. To give you a better example or idea of this is, here we have a make DOFs where we get one degree of freedom per vertex. And as you can see down here, then you get some contiguous space of 1 degree of freedom per vertex. But be careful here. Here you can see the unstructuredness, right? This indexing of these buffers, while it is in contiguous space, doesn't tell you anything about the physical locality of these vertices, right? In this case, the indexing was chosen so that the graph looks nice, right? And right, this is an example for vertices. But what you could also do is, for example, here we have 1 degree of freedom per cell. So here we just get 3 buffer entries for these 3 cells. Okay. And these are buffers in HighPerMeshes. And next up, let's get to dispatchers. I think dispatchers are really cool. They actually provide a true separation of parallelization from implementation of the solver. So I think this is the feature that really makes HighPerMeshes a domain-specific language, because the idea here is that you have this dispatcher execute, and in here you put your kernel. And the kernel is what the user writes, right? So the natural scientist or engineer, he writes a kernel that is independent of any parallelization technology or whatever. So independent of parallelization technology. And in this example, we have a sequential dispatcher, which we initialize and then execute. So these kernels then would just be executed sequentially. But what you then could think about is a distributed dispatcher that somehow internally distributes these kernels and takes this runtime object, which I explained. So just essentially the information about the backend that we're going to use to dispatch, to distribute our kernels, and then the dispatcher execute remains the same, right? So also all the calls inside of so all the kernels inside this dispatcher execute call remain the same. And so you get the same code, and now it is distributed. And I think this is one of the main features of HighPerMeshes. Okay. So this is the idea behind dispatchers. Now let's look at kernels. So how do kernels look like in HighPerMeshes? We have these statements for each entity, which means that we want to iterate over each entity in this range here. So mesh get entity range 2 means that we want to get each entity in the second dimension of this mesh. So in this case, all cells in this mesh, right? And in the next line, we see a so-called access pattern. What does this mean? So your kernel is defined in terms of a singular entity, right? So a local view on a singular entity, and you have to provide certain access patterns for parallelization, for example, that specify which buffers you want to access and which entities inside this buffer you want to access. So for example, in this, we specify that we just want write access to this buffer, which gives us certain advantages in parallelization, right? Your dependency graph gets a bit easier if you only want to write data. And this vertex here means that in corresponding to the cell that we're looking at in this kernel, we want access to the buffer entries corresponding to the vertices in this kernel. As you can see here in the example, right, you have this is your current object that you're iterating over. So, or let me say, in your iteration domain, this is the entity you're currently looking at, and you want buffer access to these vertices corresponding to the cell. And here, lastly, we have this lambda function to which is then the user-defined kernel, right? And it is done, and then you get parameters that you can use in this lambda function. So this always looks the same. And the cell here then gives you access to the topology and geometry of the entity you're currently looking at. This auto step here is a time step. So an iterative solver has a certain number of time steps or iteration steps it iterates over, and you can also access this information. I don't want to go into much detail here. And this local view object is a helper object that will give you access to the actual buffer entries that you want to access here, right? And let me show you the example a bit further, right? So currently we are iterating over this entity, get access to these buffer entries, and then we iterate over the next entity, then get other buffer accesses corresponding to these vertices, and lastly, we iterate over the last entity in this mesh, the last cell in the mesh. Okay, and this is how kernels would be implemented in HighPerMeshes. Note that this can also be a bit more complicated than this, right? As I mentioned in the introduction, you may also iterate over entities that do not lie on a boundary or that do lie on a boundary. You can specify this with these functions here, or we have other iteration methods. What is also possible is that we want to iterate over all all cells, for example, and for all of these cells we want to iterate over their edges would be a possibility. Okay, so this is how kernels look in the language. So now we have seen all the language features, and well, now you might think, okay, these are cool language features, but can you actually do something purposeful with them? So I actually want to give you an example of an application that you can implement in HighPerMeshes. For this, we chose the matrix-free solver for the Poisson equation. So here you have the matrix-free, you have the Poisson equation with some Dirichlet boundary on some computational region, and the discretization of this will lead to a system, a linear system of equations ax equals to b. And because this a has certain properties, this will lead to a convex minimization problem that looks like this. And in this example, I want to show you only a certain part of this, which is this assembly of this right-hand side B here. Okay. And how would you go about this? Here we have our mesh again, right? And corresponding to this mesh, we have a vector B that just has these vertices 0 to 4, and this G stands for global. So the actual index is in the global total mesh, and we have an appropriate storage corresponding to this. The notation is a bit the notation means here in this case, this V0 means the data corresponding to vertex 0. Okay, and you can then iterate over your mesh, and you get some local kernel now with local vertices. And the way this works is this assembly of the right-hand side is that you then can compute something with ansatz functions and partial integration for these local kernels. So only in terms of this entity here from 0 to 2, and you would then store it, the values you computed for these vertices, you would then store in the global vector corresponding to the global index of the element, right? So in this example, we go from 0, 1, 4, but look at the local elements 0 to 2, and you then would add the corresponding, the values you computed to the buffer in the global mesh. Okay. And then you go to the next element. Here you have 1, 3, 4, and you add 1, 3, 4 to 1, 3, 4. Now your other new local values that you computed for this triangle here. Okay. And then you do this for the third one as well. And now how do you implement this in HighPerMeshes? Here we have a kernel. Here you can also see this, the idea behind this dispatcher execute, right? So you have this dispatcher execute and you put your kernel in here. And the way this works is you want to iterate over all cells. This is what was this mesh get entity range before. And then you have an access pattern where you want to access corresponding to the cells, the vertices of B. And here you have your kernel again. Here we have then the calculations of these values in terms of this cell here, right? I don't want to go into detail here, and but you can then calculate the appropriate values, and then you iterate over all vertices. Here you see this get topology, this topology object, and you want to get the entities of dimension 0 corresponding to the cell. So what this means here is that you want to get the vertices of this cell, okay? And then you write to this, this local view of B. This is why here we only use the local indices, because as I mentioned, this is a local view of B. Then you can just add the value to that. And this way you can formulate kernels in terms of in HighPerMeshes. Okay. And now that we've seen an example, a fairly simple one, I also want to show you some experiments that we did regarding scalability. And first up, let me get to the experimental setup. So we have a system with 2 sockets per compute node, CPUs with 20 cores on this Intel Omnipath networks, and we have 20 threads per socket. And for the purpose of these experiments, we have 2 backends with ACE, which is a scheduling library. If you're interested, here's a link to this library. And we use, in this case, GASP-CXX to distribute the code. Also here you can find the way to, you can find the distribution backend. And we have 2 backends, one using a thread pool using POSIX threads, which are provided by ACE, and one backend in OpenMP. So the idea behind these 2 backends were to show that the domain-specific language is not so to say, catered to one specific backend technology. So you could also think about, for example, OpenCL backends in the future here, and it would still work with the same language features, so to say. Okay, and now our experiments. We have 3 kernels from 2 applications. At this point, I have to say that I'm a computer scientist, so I'm not an expert on the applications on this side. So if you're interested in the specific applications, you can find more information about this in the paper. And here we have 2 applications, this matrix tree solver. Here we're going to look at the assembly of the matrix vector product, which is this AX. And this continuous Galerkin time domain Maxwell solver. Here we'll look at the Maxwell volume and surface kernel. These kernels have different properties regarding their workload and their the entities they iterate over. So they actually have different properties which will impact their performance. And we do this on, we iterate over 1,000 time steps in this case, and we iterate over a mesh of 400,000 tetrahedra. So this is a normal problem size targeted by HighPerMeshes. Okay. So let's look at the results. Here we see the speed up for this thread pool. Here we have the 3 examples and we go from 1 to 32, and we go from 2 sockets to 32 sockets. And the reference to this is always the, for our 2 backends, we also have run it on 1 socket, and there we take, we compare it to the faster one. So on 1 socket, the OMP backend was faster, then we would still compare these speedups to the OMP backend on 1 socket if the OMP backend was faster on 1 socket. Okay. And here you can see the speedups, and they are quite good. So with 28, I think very close to the optimum of 32. And with 21 as the worst for the matrix vector product. And in OpenMP, it would look like this. So as you can see here, the peak speedups are a bit better than the thread pool, but the matrix vector product is quite a bit worse, with 15.39 compared to 21. A possible explanation for this is that actually the matrix vector product has a workload that is smaller than the other examples, because in the volume and surface kernel, we iterate over 20 degrees of freedom for each cell, while on the matrix vector product, we only iterate over we only look at 1 degree of freedom. So I think that the workload here might not be sufficient enough to get a speed up close to the optimum. Okay. And with this, I want to come to a summary. So we have seen that HighPerMeshes is an embedded DSL that provides high-level abstractions for iterative matrix-free algorithms on unstructured grids. And I think that this, as I mentioned in the talk, this executor model, these dispatchers, allow truly a true separation between the implementation of a solver and a parallelization backend, right? So we can actually separate the work of the engineer or natural scientist from that of the computer scientist that parallelizes the code in the end. And I think this is the main feature here. And also we have seen that for the two backends that we provide, that the distribution and parallelization of HighPerMeshes codes scales. Okay. And last slide, I want to thank you for your attention. I'm Stefan Groth, and you can, if you're interested, you can contact me via this email here. And I also want to point out that HighPerMeshes is available publicly and open source under this link. So if you're interested, you can check this out, and user feedback would be greatly appreciated. So I would be thrilled if you took a look at HighPerMeshes. And also I want to point out that the work was supported by the BMBF. Okay, then thank you very much, and I'm open for questions.
Thank you, Stefan. So we do have questions actually. We don't have much time, but still, at the expense of a break, we have questions from Poria Saberi. So first question is with regards to topology. Do you support distributed storage?
Yes, we support distributed storage.
With regards to discretization, does the DLS include a simplified syntax to generate the finite dimensional spaces, discretized weak form, etc.?
I think here the abstraction level is a bit so we don't have this feature at the moment. You could implement it on top of HighPerMeshes, but we do not provide any features regarding, let's say, so we do not have yet any library implementation, for example, for specific use cases in actual applications. So
okay, and last question from this pool with regards to C++. Could you elaborate on C++ 17 specific features of the DLS?
So we make quite a lot of use of C++ fold expressions, right? So unpacking, iterating over variadic templates, or unpacking tuples with standard apply. So we make quite a bit of use of that. there is another question. If I could elaborate on how we